Hello students, this is Professor Chalai, and in this video we're going to look at molecular orbital theory. As always, you can follow along with our Chapter 8 workbook. By the end of this video, you should be able to derive molecular orbitals, or MOs, from atomic orbitals, or AOs. You should be able to describe bonding and anti-bonding orbitals. You should be able to calculate bond orders, write molecular electronic configurations, and also relate these molecular electron configurations to the stability and magnetism of various molecules. Let's get started. Now, so far, when we've talked about bonding, we looked at this overlap between atomic orbitals, right? And that's how we form pi and sigma bonds. For example, if we had, let's say, a p orbital this way, let me just draw it this way, and a p orbital that, well, it needs to overlap, right? Like that, from two different atoms, and this is one atom and the other atom, where they overlap, right? That's how we describe the bonding between them. And so in this example, these two p orbitals that overlap form what we would call a pi bond. Now, this is a useful tool, but as we know, electrons move around in atoms and molecules as waves, right? And what we know about waves is that they can constructively and destructively interfere. So let's say this is a wave, the red part's the positive part of the wave, and the blue part's the negative part of a wave. If we had a second wave, right, next to it, well, then what would happen? Well, the positive parts of the wave would add up, and the negative parts of the wave would add up as well to give you a bigger wave, right? This is constructive interference. Similarly, we can have destructive interference where if they were the opposite, they can perfectly cancel out. And so this idea of molecular orbital theory is, well, instead of just dealing with atomic orbitals or even hybrid atomic orbitals and how they overlap for bonding, what happens is the electrons are not in atomic orbitals anymore, but they're in molecular orbitals. And so they're not associated with one atom or another atom. They're spread out over the whole molecule as a molecular orbitals. So the atomic orbitals are now changed into a molecular orbital in the molecule. And so the whole molecule can be treated as a single object with its own electron orbitals, with its own electron configurations and all that stuff. Molecular orbital theory is the description of electrons as assigned to the entire molecule and not individual atoms. So no longer would we have s orbitals and p orbitals and any of the atomic orbitals. Neither would we have hybrid atomic orbitals. We have now molecular orbitals. And let's see how these would come together as two atoms come together. So let's start with the case of s orbitals. Let's say we have one s orbital here and another s orbital here for two different molecules, right? These waves have the same sign, so when they come together, they're going to add up and form one bigger s orbital. And so for this case, because they come from s orbitals, we're going to call this a sigma orbital. And if you're wondering if it has anything to do with sigma bonds that we talked about earlier, you bet it does. But here's the thing, these s orbitals, right, could either be positive sign or it could be a negative sign, right? Similarly to a wave. Let's do this. A wave could be positive sign, or as it fluctuates, it could have a negative sign. These are just called the phases of the wave. And so if we had two of these s orbitals, let me create some space here. If we had two atoms, one s orbital was in a certain phase, let's say the positive phase, and the other one was in a negative phase, when they add together, what do you think they would look like? Well, let me create some space over here to draw it. Exactly where they meet, in the middle here, they'd cancel each other out, right? Positive wave, negative wave cancel each other out. And so what would happen is a little bit of the red would be left over sort of over here, a little bit of the blue would be left over over here. And so this no longer looks like a pi orbital, or pi bond, if you will. So we'll call this a sigma orbital. We'll call this a sigma anti-bonding orbital. This little star here means anti-bonding. Why do we call it anti-bonding? Well, look at this one. This is a sigma bonding orbital, right? Because the electrons are between the two nucleus holding it together. However, this one, the electrons are separated. It's kind of like it doesn't want to be associated with the bond between two nucleus. So we'll call it an anti-bonding orbital. So that's what happens when s orbitals come together from atoms. Let's look at a case for p orbitals. So we know that p orbitals could look like this along the x-axis, or like this sort of along the y-axis, or in and out of the page along the z-axis. So we'll look at each of those cases separately. Let's look at a case with the p orbitals along the x-axis, right? So this is our x-axis. We'll have one atom here, the nucleus of the atom, and this will be the positive part of the orbital. Let's draw it this way. The two positive parts for the p orbital will be inwards, the two negative parts will be outwards, right? If you add this together, you probably already see where this is going. The middle parts, where it's two positive parts of the orbital, will make one bigger positive part, kind of like this. And then the two negative parts, nothing cancels them out, so they remain negative, like that. And so this, what does it look like? Well, this looks like one big ball in the middle, kind of like a sigma orbital, right? So we'll call this a sigma orbital as well. But let's look at the other case, the opposite case, if you will, we have a nucleus here, a nucleus here. For one of the atoms, we have the positive part of the px orbital inside and the negative part outside. But this, the second atom, we have the negative part there and the positive part there, just to give you an idea of what it might look like. So what would happen in this example? Well, as you would guess, the positive and negative parts where they meet in the middle will kind of cancel each other out. So we'll have maybe a little bit of positive left over here and a little bit of negative left over here. And then for these positives and negatives, nothing cancels them out, so they remain untouched, right? This is the opposite of what we had below, so we'll just also call this a sigma antibonding orbital. Antibonding because there's nothing in between holding the atom together. There's no bonding electrons. So here are two cases where we can form a sigma bond between two s orbitals, right? This is what they look like. The sigma from two s orbitals would look like this, just one big blob. The sigma antibonding orbital from two s orbitals sort of just looks like this, little bits just left over after the bits in the middle cancel out. If you have two p orbitals and they come together to form sigma orbitals, you can have the sigma bonding that kind of looks like this, or the sigma antibonding that looks like this. Now let's look at the other case where we have the p orbital along the y-axis, right? So we'll have our nucleus here, another nucleus here, and let's use the case where the positive parts of the wave are sort of pointing up, the negative parts are pointing down. As you would probably guess, the two positive parts would sort of add up, right, to make a bigger positive. The two negative parts would add up to make a bigger negative, and we have a situation like this. Now this just looks like one gigantic p orbital, and so we're going to call it, if you might have guessed, a pi bonding orbital. All right, let's look at the opposite case where the signs of the waves were slightly different. Okay, there we go. So in this case, we'll have the positive part pointing up, and for one, the positive part pointing down for the second. And so we have this situation. Well, what would happen here? Exactly sort of where they meet in the middle, right? They would cancel each other out. Let me just try to draw them slightly bigger so we can see. So where they meet in the middle here, they'll cancel each other out, right? And then there'll just be bits of it left over in the corners. So let me see what that would look like. So if they cancel each other out, that's much too big. We'll have a little bit left over here, and a little bit left over here, and then left over here, and a little bit left over here. So instead of being in between the two atoms, forming a bond, pulling them together, there's nothing in the middle here, right? It's an antibonding orbital. And so we'll call this a pi star orbital, or pi antibonding orbital. And if the bonds are going in and out of the page, you'll have the same situation like this. Just imagining it, the bonds are going in and out of the page instead of up and down on the page. That's a little bit harder to draw, but actually, I'll make an attempt at drawing it. So in the bonding case, right, the bonds are coming in and out of the page. So if you can imagine going this way, in and out of the page, there's my pi bonding orbitals for the two atoms, because the pi bonds align and they add up. So this would be pi orbital. And then when they cancel each other out, there'll be a little bit of positive left over there, a little bit of positive left over there, and negative left over there and there. It's really hard to draw this, but imagine this is going in and out of the page instead of slanted, I guess. And so this would form the pi antibonding or pi star orbital. So that's what we get. And we're only going to stop at these cases. But when s orbitals come together, so these here for s orbitals come together to form molecular orbitals. These are when the p orbitals come together, px orbital if you will. And these are when the py and pz orbitals come together. They form these molecular orbitals. Molecular orbitals span the whole molecule, but we're only going to deal with the simple case where our molecule is just going to be two atoms, right? To see what these look like in much bigger molecules, I can't draw them on here. It's going to be too much. If you'd like to see what they look like in some bigger molecules, I can show you images of them though. All right, so now that we have an idea of what they look like, let's think about energy, right? When orbitals come together, they're always going to form bonding orbitals that are lower in energy and anti-bonding orbitals that are higher in energy. So let's look at the case with an s orbital. So let's say you have the y-axis is energy, right? And you have an s orbital here. So let's say it's a 1s orbital. This is the energy that it has. Let's say there's another 1s orbital over here with this energy. When they come together, they'll form a sigma bond that's lower in energy, so a sigma bonding orbital, and they'll form a sigma antibonding, so I'll label it sigma antibonding, that's higher in energy. And since these came from 1s orbitals, I'll label these as 1s subscript. So that's how we label them. So let's scroll all the way back here, and this is what this is showing you. Let's say you take an atomic orbital and another one at the atomic orbital, you'll form two molecular orbitals, right? And one will be lower in energy, that's the bonding orbital. One will be higher in energy, that's the antibonding orbital. So the one that's lower in energy, it's like this one, the bonding orbital. The one that's higher in energy, it's kind of like this one. All right, what about when p orbitals come together? So we know there's always going to be three p orbitals. So if three p orbitals come together with another three p orbitals, so there's 6 orbitals total, you must always form 6 molecular orbitals from those. And based off of these diagrams that we've shown right here, you should form one sigma orbital, one sigma star orbital, and 1 2 pi orbitals, and 1 2 pi star orbitals. So let's look at it. Remember, as I said, all of the bonding ones will be lower in energy, all of the anti-bonding ones will be higher in energy. So here we form 1 sigma orbital, 2 pi orbitals, 2 pi star orbitals, and 1 sigma star orbital. I hope that's all starting to make sense. These are lower in energy, these are higher in energy, because the anti-bonding energy orbitals will always be higher in energy. Okay, so for bonding and anti-bonding orbitals, we went over that. And then let's just mention briefly what are nodes. So in all of these anti-bonding orbitals, you'll notice that there's an empty space. Let me zoom in. There's an empty space in the middle, right? There's an empty space in the middle there. This is a sigma or star. There's an empty space there. There's an empty space in the middle there. and there's also an empty space in the middle here. Those are the nodes. The nodes are sort of the space in between the atoms for antibonding orbitals where there are no electrons. So bonding orbitals hold atoms together. Antibonding pushes atoms apart because there's nothing holding them together. And my handwriting is starting to go crazy. Nodes, I'm trying to write too fast is the problem, is the empty space in antibonding orbitals. Actually, you don't even have to, other orbitals other than antibonding orbitals can also have nodes. For example, let's look at this situation right here. If I can draw it cleaner, we had an orbital like this, an orbital like this, with a nucleus in the middle. There's actually a node here too. Even though this is a bonding orbital, there's a node here as well, where there's no electrons, because electrons are either up here or down here. So you could have nodes in like p orbitals and stuff as well. But for these examples, we're going to look at just nodes in antibonding orbitals, which is just in between the two atoms. All right, we'll come back to this in just a second. Highest occupied molecular orbitals. All right, so now we have an idea of when s orbitals come together, they form two sigma orbitals. When p orbitals come together, they form 4 pi orbitals and 2 sigma orbitals. And how to figure out exactly what their energies are, we use these rules right here. If they're coming together from boron, carbon, or nitrogen, and the two p molecular orbitals form have this sort of energy order, right? There's 2 pi orbitals that have the same energy, right? These are the pi orbitals. They will always have the same energy. That's why they're on the same level here. And here, the pi star orbitals also have the same energy, the same way the p orbitals have the same energy. But in the case of boron, carbon, and nitrogen, the pi orbitals are lower in energy, then the sigma orbitals, then the pi star orbitals, then the sigma star. In the case of oxygen, fluorine, or neon, when they come together, the sigma is lowest in energy, then the pi star, then the sigma star. So for the example above here, where the sigma is lowest in energy, then the pi star, then the sigma star, that's probably a combination of either oxygen, fluorine, or neon. Here are some additional rules to consider when we're drawing molecular orbital diagrams. If you have larger electronegativities, you're typically lower in energy. So in this example here, I drew these as having the same energy, but if one of these was more electronegative than the other, then they would be slightly lower in energy, right? They'll probably start off somewhere here, for example. I'll show you an example of where that actually comes into play. I just wanted to put it in there. And then we'll come back to bond order, but actually let's talk about bond order right now. The bond order is basically counting the number of bonds in a molecule. And to do that, you take all of the electrons in the molecular orbitals, all of the electrons in the antibonding orbitals, so bonding versus antibonding, subtract them, and divide it by 2. In this way, you can get single bonds, double bonds, but you can even get half of a bond, which is not something you can get with like Lewis structures or any of that stuff. And finally, after we have our molecular orbitals, we fill them in with electrons the same way we fill atomic orbitals. Lowest energy first, then highest energy. So let's look at this example up here. We started with 2 electrons in this atom and 1 electron in this atom, so we need 3 electrons in the molecule. And this is our orbitals. We put 2 in the bottom here, 1 up here. Those are our 3 electrons. Similarly, in this example here, we started with 4 over here and 3 over here, so that's 7. So we filled 2, 3, 4, 5, 6, 7. And the same rules apply as do with atomic orbitals. That is, you fill them with unpaired electrons first if they're on the same energy level. So for example here, I fill these with single electrons first, and then I paired them up because they had the same energy. All right, let's do some for practice, and hopefully the more practice we do, the more easy this becomes. And I'll hit back paramagnetism and diamagnetism in just a second. So let's look at the case of hydrogen, H2, but with a negative charge. So H2 with a negative charge. Let's draw the MO diagram first, and then we'll come back to bond order and those other things. Okay, H2 with a negative charge. Hydrogen we know has 1s orbitals, right? If we're looking at energy going this way, 1s orbitals. So when they come together, it's going to form an orbital that's lower in energy and an orbital that's higher in energy, right? The lower in energy, 2s orbitals coming together, is a sigma orbital. And the one that's higher in energy is going to be a sigma antibonding orbital or sigma star orbital. And just to keep track of where it came from, we're going to put a 1s there and a 1s there just to show that they came from 1s orbitals. Okay, we're looking at H2 minus. H2 minus, how many electrons does it have? Well, every hydrogen has 1 electron, and there's a negative charge, so that's another electron. So we have 3 electrons to put in, so let's do that. 1, 2, 3 electrons. That's it. This is our molecular orbital diagram for H2 minus. Now, let's look at the bond order. Now, the bond order, as we talked about here, it's the number of electrons in the bonding MOs subtracting the number of electrons in the antibonding MOs divided by 2. So, the bond order will be number of electrons in the bonding orbitals. This is our only bonding orbital. There's 2 of them. Minus the number of electrons in the antibonding orbital, that's 1, all divided by 2, and so this will give us a half. So the bond order here is a half. What does that mean? Well, it means that if we have this molecule H2 minus, right, H, all with a negative charge, there's actually a half a bond between them. I know, it sounds strange. What is a half a bond? But according to molecular orbital theory, we can have half a bond. Okay. So is this H2 bond stronger or weaker, H2 minus bond, stronger or weaker than just regular old H2? Well, in regular old H2, we would only have 2 electrons instead of 3, so we wouldn't have had this electron here in this antibonding orbital. So the bond order for H2 would have been the 2 bonding electrons minus 0 antibonding electrons over 2, which will just give us a value of 1. And we know that. We know that hydrogen has a single bond in between. For H2, there's a single bond between the hydrogens. So, if H2 minus has a half a bond, H2 has a full bond, which one's stronger? Well, as you might suspect, H2 minus is weaker because it's the amount of bonds that it has is less than H2. Okay, now let's look at this idea of whether the molecule is paramagnetic or diamagnetic. Well, what do we mean by paramagnetic or diamagnetic? In paramagnetism, we have a molecule that is attracted to a magnetic field because of unpaired electrons. So if a molecule has unpaired electrons, it's going to be paramagnetic. And for diamagnetism, it's a molecule that is unaffected or weakly repelled by a magnetic field because it has no unpaired electrons. So in this example of H2 minus, there's 1 unpaired electron in the molecule right there, which I just erased accidentally. And so H2 minus would be paramagnetic. All right, what about bond length? H2 minus, bond length to be longer or shorter than H2? Well, we talked about how when something has more bonds, the bonds are stronger and it pulls the atom together more. So if H2 has a weaker bond, or right, because there's only half a bond, then the bond would be longer. So this means longer bond than H2 simply because it's a weaker bond, right? Okay, so that's an example of how we can use molecular orbital theory to understand bond order, bond lengths, and whether things are paramagnetic or diamagnetic. Okay, so what about the electron configuration? We know that in atoms, we write the electron configurations like 1s2, 2s2, 2p, and so on and so forth. And that's for atoms. But now we have molecules with molecular orbitals. So what would their electron configurations be? Well, it would be the same thing, right? We have a sigma orbital, that's the label, sigma 1s, and it has 2 electrons in it. So we'll write it like sigma 1s with 2 electrons. Then there is a sigma 1s star with 2 electrons. So there's a sigma 1s star with 2 electrons. Sometimes people put these in parentheses so that you don't confuse the star. Right, that's the electron configuration. Electron configuration. Okay, and this is for H2 minus, remember. Now, let's look at number 9. Try this one by yourself and answer the same set of questions. Now we're looking at H2 plus. All right, so if you haven't yet, please pause the video now and do it and answer all of these questions on pause, and I'll do them with you. All right, we're looking at energy and with hydrogen, so we're starting with 1s orbitals only, and as you would expect, when they come together to form molecular orbitals, we'll form a sigma orbital that's lower in energy from the 1s orbital, and a sigma star orbital or antibonding orbital that's higher in energy, again from the 1s. H2 plus, how many electrons does it have? Well, each hydrogen has 1, but we need to remove 1 because it's a positive charge, so there's only 1 electron in here. That's it. What's the bond order? Bond order is the number of bonding electrons, which is 1, minus the number of antibonding electrons, 0, divided by 2, which is therefore also half. So H2 plus is also half. The bond order is also half, which means this bond will be weaker than H2 because H2 has a bond order of 1. Is the bond length shorter or longer than H2? It should be longer. Longer than H2 simply because it's a weaker bond. And it doesn't ask for it, but is it paramagnetic or diamagnetic? Well, there's only one unpaired electron, so it's paramagnetic. There we go. All right, let's write the electron configuration for H2 plus. There's only 1 electron in the sigma 1s star, so we'll have sigma 1s, not star, sorry, just the sigma 1s, and there's 1 electron in there. That's the electron configuration. All right, let's look at number 10. Try to answer number 10 on your own. Number 10 is trying to compare what you would get from the Lewis structure versus what you would get from molecular orbital theory for oxygen, O2. And let's see how those compare. Okay, if you haven't paused the video and done this already, please do so now. Okay, let's look at O2 for the Lewis structure. We've done this a few times, right? There's oxygen bonded to oxygen, and we would have this many electrons, valence electrons. Now this oxygen on the right doesn't have a complete octet, so let's share with 2 on the left. Let's have that situation. Okay, According to the Lewis structure, how many bonds does O2 have? Well, according to the Lewis structure, the bond order is 2, right? There's 2 bonds. We'll see how this is different with molecular orbital theory, if it is. And is O2 diamagnetic or paramagnetic? Well, diamagnetic versus paramagnetic has to do with unpaired electrons. But here we have the bonds. They're always paired, right? Each bond is a pair of electrons. Here we have a pair, so it's not unpaired. Here we have another pair. Here there's a pair. Here there's a pair. So there's no unpaired electrons, according to the Lewis structure. So, according to the Lewis structure, this should be diamagnetic. Just as a heads up, this is actually incorrect based off of experiments. An oxygen molecule, according to experiments, is paramagnetic, but according to this Lewis structure, we don't know where the unpaired electron is coming from. Everything looks paired. All right, now let's look at the MO diagram for O2. So for O2, the MO diagram, we're going to go up this way in energy. Oxygen, we know, has 1s, 2s, and then 3 2p orbitals, kind of like that, increasing energy. Now, I'm going to ignore all of the, well, I'm going to do all of it, and then I'm going to show you why we can ignore it later. So here's another 1s, 2s, and 2p orbitals for the second oxygen atoms, because there's 2 oxygen atoms coming together. All right, so maybe we should bring these a little bit closer. Maybe that close. Okay. So let's combine our 1s orbitals. So 1s, 2s, 2p, 1s, 2s, 2p. When we combine our 1s orbitals, right, we know we get a sigma and sigma star orbitals. One higher, one lower in energy. So this is sigma from the 1s. This is sigma star from the 1s. Same for the 2s orbitals. We get an orbital that's lower in energy and an orbital that's higher in energy. Again, they're s orbitals, so we'll get sigma 2s and sigma 2s star. All right, the p orbitals, things get a little bit crazy. Let's move up a little bit so I can create some space. I'll use a different color for this one. Okay, for oxygen, let's scroll up all the way here to see the energy orbitals. For oxygen, we'll have a sigma, then 2 pi's, then 2 pi stars, then 2 sigma stars. So that's the order of the orbitals that we need to create. So we'll start with a sigma, 2 pi's, they're all lower in energy. Then we go to 2 pi star, that's higher in energy. Then a sigma star, that's higher in energy. So this is sigma, comes from a 2p. This is a pi that comes from a 2p. This is a pi star that comes from a 2p. And this is a sigma star that comes from a 2p. So that's how we label them. Okay. So those are all of our molecular orbitals waiting to be filled with electrons. Let's fill them with electrons. How many electrons should oxygen have? Well, each oxygen has 8 electrons, and there's 2 of them, so we need to fill this with 16 electrons. So let's do that, and I'll use a nice green to fill them. So 1, 2, 3, 4, 5, 6, 7, 8 electrons, 9, 10 electrons. So far, so good. Remember, when they have the same energy, you fill them with single unpaired electrons first. So 11, 12 electrons, 13, 14 electrons, 15, 16 electrons. Those are all my 16 electrons. All right, things are looking good so far. Let's look at the bond order. The bond order is all of the bonding electrons minus all of the antibonding electrons divided by 2. So let's count all of the bonding electrons first. We have 2, 4, 6, 8, 10. So that's 10. How many antibonding electrons do we have? Here's an antibonding orbital, so that's 2. Here's another one, 4. Here's 2 more, 5, 6. So minus 6 divided by 2. 10 minus 6 is 4, divided by 2, we get 2. So far, this is good. This is checking out with Lewis structures. We have a double bond. According to this, we also have a double bond, also, although it's a little bit difficult to figure out from this diagram. What is left? Diamagnetic or paramagnetic? Well, here's the difference. There are 2 unpaired electrons up here. So according to that, this should be paramagnetic. And this is where molecular orbital theory is a little bit more powerful than just Lewis structures or valence bond theory or any of that. It actually gives us an idea of whether molecules can be paramagnetic or diamagnetic, because we actually take into consideration the spins of the electrons when they form orbitals. Now, in a case like this, we could have ignored the 1s stuff because they're core electrons, and we can probably should have only focused on the valence electrons. So the 2s and the 2p orbitals coming together. But there we have it. The molecular orbital diagram for oxygen. Let's erase these circles. There we go. That's a molecular orbital diagram for oxygen. Let's write the electron configuration for oxygen for the molecule, right? We'll have the sigma 1s with 2 electrons and the sigma 1s star with 2 electrons, right? Which we've already erased. Now we go to the sigma 2s, right, with 2 electrons, and then the sigma 2s star with 2 electrons. Then what's next in energy? The sigma 2p, right here, sigma 2p. So I'm using a different color, but that's okay. Sigma 2p with 2 electrons. What comes after that? What's higher in energy? We have the pi 2p with 4 electrons in it. The pi 2p with 4 electrons. Then comes the pi 2p star with 2 electrons in it. Just to show you here, that's a pi 2p star with 2 electrons. And so this whole thing here is the electron configuration of the O2 molecule. All right, how about you try one? Try the MO diagram for N2 minus. Remember, to figure out what the order of the energies are up here, we can use the table over here. And so for N2, we're looking at these set of rules where the pi bonding comes first, then the sigma bonding, then the pi antibonding, then the sigma antibonding. So that's the order for the 2p stuff. All right, try that one on your own first, and then pause the video and I'll go it over with you. Okay, let's look at this. We have our energy going this way, and I'm going to start with the 2s orbitals. I'm ignoring the 1s because we know that they're core electrons. We don't need to worry about them. There we go. All right, this is 2p. The 2s comes together. The 2s come together to form a sigma and a sigma star. Right, we'll label them with 2p. And we need to create some space for the 2p orbitals. Sorry, these should all be 2s. It's sigma orbitals. Why are they coming from 2p? They should be 2s. There we go. All right. For the 2p, we talked about how the lowest in energy would be the 2 pi star. Let's create even more space. There we go. Then the sigma, then the 2 pi, the pi, then the sigma, then the 2 pi star, then the sigma star. So that's the order. Let's label them. Pi from the 2p, sigma from the 2p, pi star from the 2p, and then sigma star from the 2p. All right, let's fill these with electrons. How many valence electrons in N2 minus? Remember, we're only looking at valence electrons now because I've ignored the 1s. Those are core. So each nitrogen has 5, and there's 2 of them, and then there's 1 extra for the minus sign, so those are 11 electrons. So let's put 11 electrons in these orbitals. We have 1, 2, 3, 4, 5, 6. filled singly unpaired first. 7, 8, 9, 10, 11. Okay. Let's look at the bond order. Number of bonding orbitals, we have, let's circle them, 1, 2, 3, 4, 5, 6, 7, 8. Antibonding orbitals, we have 2 here and 1 here, that's 3, divided by 2. That gives us 5 divided by 2, or 5 over 2 is basically 2.5. Alright, well, they're asking us to compare this to N2, right? Would it have a stronger or weaker bond than N2? So if it was just N2, it would have one fewer electron, right? So it basically wouldn't have this electron on top. It wouldn't have that electron. Let's erase some of these to make it look cleaner. There we go. And that one. Alright, so for N2, it wouldn't have that electron on top, so the number of bonding electrons would remain the same as 8, but the number of anti-bonding electron would only have been 2, and so this would have given us 6 divided by 2, or 3. So N2 has a triple bond. And if you draw the Lewis structure, you probably could have figured that out. So N2 minus has a lower bond order, which means it's a weaker bond, right? That's weaker. But that also means that it's longer, because it's weaker. And the question didn't ask this, but if it did, N2 minus would also be paramagnetic, because there's an unpaired electron right up there. Okay, let's look at the electron configuration now for N2 minus, right? We drew it over here. So we can start with the sigma 1s with 2 electrons, the sigma 1s star with 2 electrons. Those are the core electrons, they remain the same. And then we had the sigma 2s with 2 electrons and the sigma 2s star with 2 electrons right here, right? Those are those two. Now we have the pi 2p with 4 electrons and the sigma 2p with 2 electrons. So the pi 2p with 4 electrons and the sigma 2p with 2 electrons. And finally, there's a pi 2p star with just 1 electron in it. There's the pi 2p star with 1 electron. And so this is the electron configuration of N2 minus. N2 minus. Okay, let's look at the case for neon. Try it for neon and try to figure out the bond order for neon. So energy, the 2s orbitals start here, 2p orbitals, there's 3 of them, is over there. When they come together, the s orbitals form a sigma and a sigma antibonding. So sigma, sigma antibonding. They come from the 2s, so let's put 2 s's there. What about neon and the 2p orbitals and their energy orders? Let's scroll up. Neon is here. Their energy orbitals are sigma, then pi star, then sigma star. So let's do that. Right? That's sigma, then 2 pi's, then the pi stars, then the sigma star. Little dashes show how they come together. All right, how many electrons, valence electrons in neon? There's 8 per atom, so 8 to 16. So let's fill 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, things seem to be going good so far. What's the bond order? Well, let's count all of the bonding orbitals. 2 here, 4, 6, 8. So we have 8, which means the other 8, because there's 16 total, right? The other 8 will be antibonding. We divide by 2, that gives us 0. Neon has a bond order of 0. What does that mean? Well, it means that neon doesn't form a bond with neon. Of course, this is something you could have told me, because you would have been able to tell me that neon is a noble gas. It doesn't form bonds with anything. So why are we worrying about all this? But I wanted to show you how, from a molecular orbital theory point of view, it tells us that neon shouldn't form a bond. All right, now let's look at the electron configuration for neon. It's pretty much the full set. We have sigma 1s with 2 electrons, sigma 1s star with 2 electrons, sigma 2s with 2 electrons, sigma 2s star with 2 electrons. And now for the p orbitals that come together, we need to remember the order, right? There is the sigma 2p, then the pi 2p, then the pi 2p star, then the sigma 2p star. So sigma pi sigma. So sigma 2p with 2 electrons, pi 2p with 4 electrons, pi star 2p with 4 electrons, and sigma star 2p with 2 electrons. And that's the electron configuration for neon. Okay, let's you can try Cn minus on your own, and also NO on your own. What else do we have here? Yeah, do those two on your own, and if you encounter problems with them, just send me a message and I can go over them with you. But now let's look at number 15. Right? Number 15, they're asking us to draw the electron orbital diagrams for transition metals. So these are just atoms, not molecules. So we're not looking at molecular orbitals, just atomic orbitals. And we're trying to predict whether these are going to be diamagnetic or paramagnetic, because molecules can be diamagnetic and paramagnetic, atoms can be diamagnetic and paramagnetic. And so for this, I'm just going to do one as an example for you. I'm going to do scandium. So scandium is a first row transition metal, and so we know that the electron configuration is going to be argon, then it's going to be 4s, then 3d, 5, yep, there we go, and so on. Now scandium has 2 electrons in the 4s and 1 in the 3d. So what do you know? Scandium is paramagnetic. Why? Because there's this unpaired electron right there. So do this exercise with all of the atoms in the first row of the transition metals, and we'll see which ones are paramagnetic and which ones are not. But that will bring us to the end of this topic on molecular orbital theory. And finally, actually, let's come back to this idea of highest molecular orbitals and highest occupied molecular orbital and lowest unoccupied molecular orbital. They are exactly what the names suggest. So highest occupied molecular orbital is a molecular orbital that's occupied and has the highest energy. I know, it sounds strange, but it is exactly what it is. And so in this example right here, we look at the highest energy orbital that's occupied, and it's that one, those set over there. It's the pi 2p. This is the highest occupied molecular orbital, or HOMO. Now, the lowest unoccupied molecular orbital is exactly what it means too, right? Is exactly what it says. It's a molecular orbital that's unoccupied with the lowest energy. So here we look at an unoccupied orbital. So shouldn't have circled both. I should have circled this one. That's the occupied orbital that has the highest energy. And then this orbital is unoccupied and it has the lowest energy of all the unoccupied orbitals. So this is again a pi 2p. It's the lowest unoccupied molecular orbital. It just so turns out that in this example, the HOMO, the HOMO, and the LUMO, LUMO, have the same energy. Let's look at some examples that we did down here. Let's look at the example of, what was this? N2 minus, right? There we go. The highest occupied molecular orbital was, let me erase these lines. Okay. This guy here, this was the highest occupied molecular orbital, right? It's occupied and it has the highest energy. And this right here is unoccupied, and it has the lowest energy of all the ones that are unoccupied. So this is the LUMO. Homo LUMO. All right, so that will bring us to the end of this chapter. I know it might seem like a lot of diagrams and arrows, but just take your time drawing them. The neater you draw them, the clearer they might become. But just know that when atomic orbitals come together from two atoms, they form molecular orbitals. And this is the idea behind molecular orbital theory, and it's a little bit more powerful than the things we've been looking at so far in this chapter, like valence bond theory and so on and so forth. We talked about the shapes of them and why we have, for example, 2 pi and 1 sigma when p orbitals come together, right? And also why the bonding orbitals are lower in energy, the anti-bonding orbitals are higher in energy when they come together, and also exactly the ordering. The ordering depends on what atoms we have that are come together. All right. If you have any questions about this section, please let me know. We'll wrap up chapter 8 here. In the next video next week, we'll begin chapter 9. I'll see you then. Bye.